Hello, in this video I will show the design of model predictive control for boost converter. Here the conventional boost converter. Uh, we have to design model predictive control for input current or output voltage control of boost converter. So first we need system parameters, we need derivative equation of the converter. I would like to talk about both finite control set, model predictive control, and boost converter. Our control variable is inductor current, so input current of the boost converter, and we need the error function or cost function in the model predictive control here. This is the inductor current reference. It is a constant value. So it is DC quantity, and this is the predicted value of the inductor current. We need the prediction of the control variable here. We can use Euler's forward method for approximation, defined here. We need this part of the equation, so the final equation is this. Here IL is the measured value of the inductor current. We will measure it, and TS is the sampling time of the control algorithm, and this is the derivative of the control variable, so the derivative of inductor current. So now we need the red part of the equation. We have to analyze the boost converter, the circuit model of the boost converter here. We can analyze the boost converter depending on the switching state, because the switching state changes the circuit diagram. So we have two possible switching states. S can be 1 or 0. So S can be on positioned or off positioned. Here the circuit diagram for S on. In this case, the inductor voltage is equal to difference between input voltage and voltage drop on RL. RL is the internal resistance of the inductor. So we can get such a function for inductor voltage. So L divided dt is equal to difference between these two values. And also when S is off positioned, we can get such a circuit diagram, and the inductor voltage is equal to this equation. Okay, now we have these two functions. We can put S for S is equal to 1 when S is on positioned. The equation will be effective. When S is off positioned, the equation will be effective on the total system. So we can get the derivative of inductor current by combining these two equations, and we have such a function for the derivative of the control variable. Then we can put this derivative equation into the prediction function, and finally we can get such a function for prediction of the inductor current. Okay, now we can design it in the MATLAB Simulink. This is our prediction function, and we need MATLAB function block. I will write code for the model predictive control. Its name is MPC boost This is the output variable. We need the switching state for the output, and we will write the input of this below. So first we can write the predictive function like here ilk1 and v in one minus s and plus il. Okay, now we have to define system variables. This is the sampling time, 10 microseconds, and 1 millihenry inductor, and the resistance of the inductor is 0.2 ohm, and we have to measure inductor current, input voltage, output voltage. Okay, so the equation is dependent on the switching state, but to evaluate this function we have to use these two options here. S can be 1 and S can be 0. I am defining the possible switching states vector here. S can be 1 and 0. And instead of using the actual switching state, we have to try it. We have to evaluate it depending on the possible switching state. I am defining n here, and I will put this function into a for loop and starts 1 and end 2. Okay, now this is our predictive function, and we have to put one more. Okay, this is our prediction function. Here we can obtain the predicted value of the inductor current with this equation. Then I'm returning back to cost function. The cost function is G is equal to inductor current reference, difference between inductor current reference and the predicted value. G absolute error IL ref minus ILK1. Yeah. Okay, now we have to know the reference of the inductor current. Okay, now we obtain the cost function. This is our cost function. The control methods works depending on finding the minimum error. In the steady state, the error should be 0. In real application, it will not be 0, but the error will turn around the 0. So it means that we have to find which options are here, which options gives less error. So I will write the minimization part. Here we are calculating the error in the cost function, and if the calculated error is less than optimum G, we can determine depending on the less error by using such a minimization here, and op is equal to n and g op will be equal to g end. Okay. We have to define initial value of g op. I'm defining a big value for g op 1e6. So why I am defining such a big value? For example, when the switching state, when the for loop evaluate the one s here will be 1, and we will get a cost value. It will be less than 1e6. Okay, the control algorithm will determine the first optimum value depending on switch 1. Then in the second option, the second option is 0. It will be 0. Then it will give different value as a result of cost function. The control method, the minimization part, will check this. Which option? So when switching state is 1, the error, for example, 1 amps. After the switching state, we are calculating the second option. Then if we get less error than 1 amp, the result will be 2. So the optimum switching state will be 2 as a result of such evaluation, and we can generate the switching signal depending on this evaluation. And here the optimum switching state is determined. Here I am putting it into the result function, but we have to define the initial value of the n. We can write 1. It is not important because the equations will evaluate the function, and we will get some result depending on this. Okay, now I'm returning back to SEPIC. We have to put required, measured, and reference variables and be in. This is the reference value, and at the output of the model predictive control, we will get the switching state directly. We will not use any modulation strategy. It will generate directly switching position, and we can put some logic to here to convert it Boolean type. Okay, it seems ready. We can run the software, and yes, it is regulated to reference 5 amps. Here the red one is the reference of the inductor current defined here, and the blue one is the measured value of the inductor current, and this is the output voltage, and this is the blue one is the input voltage. Okay, now we can change the inductor current reference, but before I want to change the time scale. Okay, we can check the dynamic response of the controller. Okay, here the reference current is changed from 5 amps to 10 amps. It is directly increasing to 10 amps. But here we can analyze, yeah, the results show that the switching frequency is very high. The switching frequency is equal to half of the sampling time, the sampling frequency, half of the sampling frequency. So it is not acceptable for many application, and the accuracy of the controller may not good in such implementation. So we need to reduce the switching frequency to get proper operation. To do this, we need one more cost function to reduce the switching frequency. We can change it GIL, and we can define one more cost function for the switching state. Now I will define, then I will explain. This is our new, and the previous value. The cost function calculates the difference between the evaluated switching state and the actual switching state. So as a result of such a cost function, we will get 1 or 0 and minus 1. Because of ABS, the result of GSW will be equal to 0 or 1. Defining such a cost function will change the will allow a band. So it means that, for example, up the current error reached, for example, 5.6 amp, it allow to keep the switching position at the previous value. If the error will reach out of the band, defined band, I will show defined band, it will allow to change the switching position. In that case, the switching frequency will reduce, because, for example, if the switching state start here, up to here, the switching state cannot be changed. After here, it can change. So it will change depending on the defined value. Now we need the total cost function to minimize the error. We can write the total cost function here. GIL plus switching, and we need to weighting factor. Here the weighting factor adjusts the weight of the GSW on the total cost function. We can select any value, and it will be effective on the switching frequency. But now we need one more variable here, as old is equal to as the previous value. It will be previous value, and as old will store the s value here. So we need persistent variable as old, and if okay, now it seems to be ready. We can return back to Simulink. We have to define weighting factor. Okay, first I'm defining 0. It means that the second post variable will not effective on the system. Then I will change and we will observe the value. Okay, now weight and factor is 0 and the switching frequency is the same as previous, so it is equal to half of sampling time. We can define any value to here, but it will change the inductor current ripple here. For example, first I will try 0.5. At this point it is changed to 0.5. Yes. Now we can see that the switching frequency is changed because the period is larger than this part. So we can control the switching frequency here. Now we can try some different value. For example, 0.3. Okay. The inductor current ripple is reduced. It means that switching frequency is higher than this part and switching frequency is less than this part. Okay. We can adjust it, and I have a solution about this. It is published in one of our papers. I don't want to talk about more this. If you want to control the switching frequency, you can check the analysis in the in our paper. Now I would like to show the output voltage control, design of output voltage control. I will indirectly control the output voltage, so I will put a PI controller to generate the inductor current reference depending on the output voltage error. Okay, this is PID controller. Discrete time and PI, and can enter the KP and KI value, and also I'd like to talk about the PI controller, the selection of PI controller parameter. I am tuning manually. I'm not using any method. You can find any method in the literature. You can check, but I'm not using the methods. And we need the error between output voltage and its reference, and we have to compare it. This is V out, and can define Vref, and we can select 48 volt. Okay, now such a control method, the PI controller will generate the reference current, and the model predictive control will provide the inductor current voltage, inductor current in the output side. So I would like to put one more variable to here. Vref. Okay. We will tune the PI controller. First, I want to check the result. Okay. The red one is the reference of input output voltage. So it is regulated to its reference. The inductor current reference is around 4 amps. It's about 4 amps. And we can change, for example, 60 volt. We can check the transition time. Here, not bad results. But when I'm tuning the controller, I will put a pulse generator. I will create a step change. And 24 plus 36. So it means that the output voltage reference will change between 36 and 60 volt. And now we can run it again. We will tune this value, and we have to change the time range. Okay. This is not, it seems not good. We have to increase the dynamic response of the PI controller. We can increase it, for example, 20. Yes, it is better than before. We can increase it. We have to increase it up to see overshoot. For example, 100. We can try. Yes. There is an overshoot in both inductor current and also in the output voltage. So we can slightly reduce the value. We can try 90. Still we have overshoot. Okay. We have small. I think this is good, but we can reduce it. Okay, and we can slightly increase it. Yes, and I will try it 80 again. In the inductor current, we have still overshoot and undershoot, but here there is no too much overshoot and undershoot. If the result is enough for you, you can use these values defined here. Okay, thank you so much for watching my videos.